Okay, so now for section 3.7, we're going to look at properties of measures, which means we're going to see just how much you can deduce already just from that really minimal amount of information that we seem to have when we say something's a measure. Now, I don't want to keep saying let X be a set and let F be a sigma field and let mu be a measure on it. So throughout this section, X is going to be a set and F will be a sigma algebra on it and mu will be a measure on that sigma algebra. And I won't bother going into details as to which set or which sigma algebra or which measure. That will be a standing assumption throughout the section. Okay, that'll save me some writing and make the statements look a little bit simpler. But you should remember throughout that's what we're doing. Okay. Now, what's the difference between this and part of the definition of a measure? Who can spot the difference? We've got a sigma field. We've got a sigma algebra on X.
Goes up to n.
Yeah, that's right. So this should be easier, shouldn't it? This is finite additivity. So we know that measures work for infinite countable disjoint unions. How can you deduce that they work for finite disjoint unions, the things in the sigma algebra? What have we got available to help us?
Just throw in the empty set.
Throw in the empty set. We've done this before. It's a standard trick. Throw in the empty set with all the remaining sets. So here's the proof. Given A1 up to AN as above, we'll set AN plus 1 equals AN plus 2 equals and so on, all equal to the empty set. Then the union from K equals 1 to N of AK is actually equal to the disjoint union from K equals 1 to infinity of AK, because the remaining sets were empty, and of course everything was disjoint, and everything's still pairwise disjoint, because the empty set doesn't make things any less pairwise disjoint than they were. So countable additivity gives the measure of the union from K equals 1 to N of AK, which you could also put a dot in if you want, but you don't have to. It's the measure of the countable disjoint union and I guess I could do a bit more space. That's equal to, that's the sum from K equals 1 to infinity of mu of AK by countable additivity, as we defined it. Which is equal to the sum from K equals 1 to N of mu of AK, because mu of the empty set equals 0. And we've done it. Typical argument for deducing thing about finite unions from infinite unions. Use the empty set. Okay, so we haven't done very much extra. You probably assumed that was going to work anyway. So we've now got finite additivity deduced from countable additivity and our fact about the empty set. So now we're going to move down to the special case of two sets. Because we're now going to take two sets of the sigma algebra with one and subset of the other. So here's your optional diagram, but it does help you to see what's going on. Here's B, here's A, and here's B take away A. The rest of the set, which I shall do in red. So, how does the proof go? Oh. Actually, before I do that, this is an important property called monotonicity. Monotonicity. If I can just get the right things in the right place. The monotone set function. If you make the set bigger, then the value of the measure gets bigger. And it's pretty obvious that this one follows from the other one because we're dealing with non-negative measures here. So in case I never mentioned it, if you add a non-negative extended real number to something, the extended real number can't get smaller. Surprise, surprise. So we'll be able to deduce the monotonicity bit from the other bit, and that bit is just finite additivity in a very special case. What have we got? So clearly, B is a disjoint union so finite additivity gives this equality here. And of course, that's greater than mu of A. And that's it. So we started to pick up, perhaps more than you might have expected about measures, that you're beginning to see that already we can see that they're a reasonably good, any measure you take is going to be some sort of reasonably good measure of size, because if you make the set bigger, the measure of the set's going to get no smaller. Now for the next one, this is another property of measures, and this one's called countable subadditivity. So let's spot the difference time again. What are the two differences between this and rule 2 for measures?
The sense of disjoint.
That's right, sets don't have to be disjoint anymore. And as a result, we don't get equality anymore, we only get less or equal. So this says that and of course this actually works for finite ones as well. As usual, you can use the empty set and get finite subadditivity. You can work out for yourself what finite subadditivity means. You can either, to prove finite subadditivity, you can deduce it from countable subadditivity in the usual way by throwing in lots of empty sets. Or you can prove it the same way as I'm about to prove this one. Okay, so how do we prove this one? Because your intuition says we've got a decent measure of size, so we think that the measure of a union is going to be less or equal to the sum of the measures of the pieces. But we haven't got many tools available because the measure, all we know so far is that measures do add up correctly on finely many pieces, on disjoint pieces. We've got that. We've got monotonicity so far, but that doesn't seem to help here because, well, the union is equal to the union, and that doesn't seem to help. So what do we do? It's a standard measure theory trick. Here's yet another standard trick. Once you've seen it once, you can use it again and again in lots of settings. We convert the original union that wasn't pairwise disjoint. You replace it by some other sets which have the same union, but where they are pairwise disjoint. And here's how you do that. So you set B1 equals A1, which of course is in F. B1 we just keep as A1. B2, we throw away the redundant bit. So B2 is equal to A2 take away A1, which is still in F, of course. B3 is A3 take away the union of A1 and A2, which is still in F. And as you can see, what we're doing is we're throwing away the redundant bits. So generally speaking, for n greater than 1, you set Bn equal An take away the union from k equals 1 to n minus 1 of Ak. And that's still in F because we know sigma is a sigma algebra, so you're not going to leave a sigma algebra by doing this sort of operation. Then here are some nice things to pick up. Well, in fact, you get that the union from n equals 1 to infinity of An is actually equal to the disjoint union from n equals 1 to infinity of Bn. And Bn is a subset of An. So the measure of the union of the ANs is the measure of the disjoint union of the BNs which is equal to the sum of the measures of the BNs that's by countable additivity. And that's less or equal to the sum of the measure of the ANs by monotonicity. And we finished. So notice how we're slowly boosting ourselves up here. We started with very little information, but we were able to get finite additivity, and from that we were able to get monotonicity, and from that we've now managed to boost all the way up to countable subadditivity. And we now know that measures have got quite a lot of interesting properties. And that's any measure you ever come across, including, of course, Lebesgue measure, which I'm going to be telling you about in a bit. So to finish off this section, we're going to look at what I call continuity properties of measures. So these last two are continuity properties of measures. I won't go into detail as to why they're called continuity properties of measures, but you can sort of get the idea. We haven't defined a formal notion of sets tending to another set. There are various approaches to that. But here's a particular kind of situation you might be in. It's a nested increasing sequence of sets expanding out to some other set. So this is a nested increasing sequence of sets. And in some sense, you expect this nested increasing sequence of sets is going to, in some sense, tend to the union. I won't go into that in any formal way, but if you imagine that that's a sort of limit for this sequence of sets, it's going to be the union, then you might hope that if you apply the measure, you're going to get the right limit there as well. So the measure of this union, which you can think of as this limit, because it's a nested increasing sequence, you hope that that's going to be the limit of the measures of the ANs, and it turns out to work. Before I prove that, I just want to point out the next result and point out the difference. This one, the next result, the corollary, this time they're nested decreasing. But there's a strange addition that looks a bit artificial. So you've got nested decreasing sequence, and you would like that the measure of the intersection to be the limit of these decreasing values for the measures of the sets. So you think of these sets as they're contracting down towards their intersection, and you'd like the measures of the set to converge to the measure of the intersection. But actually that isn't always true as it stands. So there's an extra assumption in there. So what's the extra assumption that's been thrown in? Who can spot a mysterious extra assumption that's been thrown in that doesn't, yep? That's right. Now actually, it doesn't matter which of them has got finite measure. Or you only really need at least one of the sets has finite measure. So you really need at least one set. At least one of the sets has finite measure of the BK has finite measure. But, well, it doesn't really matter which one it is, because they're nested decreasing. And of course, all the interesting stuff happens later. The limit of the measures of the BN, which will exist because that's a monotone decreasing sequence of non-negative extended real numbers, that limit will exist, and it doesn't depend on the first few. So as soon as you've got one of these things having finite measure, you can just look at the sequence from then on. So you might as well assume it's the first one that's got finite measure, because you can deduce the general result from that. And the reason there's a problem with this one, you deduce this one from the other one by subtraction, but you can't subtract infinity from infinity. And that's where the problem comes. So the problem arises with infinity minus infinity, okay? Which is not allowed. You can subtract finite real numbers from infinity without doing anything wrong. Or we can certainly subtract finite real numbers from each other with certainly no problems. So the assumption mu of B1 or infinity ensures that all the numbers involved are real numbers. and then you'll have the usual adder of limits and the real numbers and so on. Okay, so we're not going to have time to prove these two today, so that's what we'll do next time. We'll prove those and then move on to having a look at how to define Lebesgue measure along with Lebesgue outer measure for subsets of the real line. Okay, so we'll stop there today.